It is one of the laws of physics that energy is conserved. You cannot lose energy. Friction might generate heat, but that is just another form of energy. In the section that we're going into, we're going to ignore the energy of heat and noise and light that might be generated, and we're just going to look at the mechanical energy. And in this case, we are going to have the work-energy equation that is just about to appear. You've seen this equation before, and this says that your final kinetic energy is equal to your initial kinetic energy plus work done. So if you do some work, you put it in, the total amount of energy is the same. The initial amount plus the work you put in is what you get at the end. Nothing has disappeared in our model in terms of light, heat, noise. Now, I like to think of this as final KE is initial KE. I'll explain these two in a moment, unless you're reading it before I get there, plus the work done or minus the work done. Some forces, if you drop something, then gravity will make it go faster. If you pull something, that will make it go faster. So if a force increases the speed, if you increase the speed, you are increasing the kinetic energy. You are putting energy in, you are increasing the energy that's there, so the work done goes into the equation as positive. I have a certain amount of energy, I put some more work into it, some more energy into it, I must add it in. In the other way, if you have a force which decreases the speed, like friction, then you're decreasing the kinetic energy. So you have a certain amount of kinetic energy, friction decreases it, it will reduce the amount of energy that you have. So it must go in as negative. I will do an example to show you how that works. In this example, a ball of mass 2 kilograms is thrown vertically downwards with a speed of 20 meters per second. 2 kilograms, 2g is the force downwards. We have air resistance of 30 newtons. That will be acting opposite to the motion, that's upwards. And the question asks us to find the speed after it's traveled a distance of 10 meters. Well, I will use the work-energy equation to do this. The first thing that I need to look at is what is the initial KE. The initial KE is a half times mass, which is 2, times v squared, and v squared is 20 squared. That is 400. It would look a little bit better if I put a bit of space between the two lines, just a bit. Right. Then we need to know something about the final KE. Well, we don't know the speed, so all we can do is say that it is a half times the mass times v squared, and that in this instance is just v squared. We've got two forces doing work. We've got gravity, we've got the air resistance. Let's look at the air resistance. The work done by the air resistance. I'm not going to worry about the plus or minus at the moment. You'll see how I deal with that. It's just force times distance, which is 300. The work done by gravity, you must get used to thinking of this as gravitational potential energy, which is mgh. mgh is the work done by gravity, but as I say, we must think of it as gravitational potential energy. M is 2, G is G, and H is 10. So that is 20 G. Now I'm going to look at the work energy equation. Final KE. Final KE is V squared. Initial KE is 400. Now we have these two forces of air resistance and gravitational potential energy. The air resistance makes it go slower. It reduces the speed, and therefore it is going to reduce the energy. We start with a certain amount of energy, we're now going to have less. So I subtract the 300. And now let's look at what happens with the GPE. The potential energy, it's moving downwards. So this figure of 20G, it's moving down. Gravity makes it move faster when it's going down. So this is going to increase the speed. It's going to increase the amount of kinetic energy. And that therefore gives us, put it in as plus 20G. From that, we now get that V is equal to 17.204, etc. But we're using G, so two significant figures is sensible in the answer. Now let's have a look at another problem with a little bit more in it. Still not difficult, but you need to think carefully when you are looking at each force. How much work does that force do? And then does it increase the energy or decrease the energy? Does it go in as plus or does it go in as minus? A mass of 5 kilograms is being pulled up a rough slope by a force of 50 newtons parallel to the slope. The friction is 0.8 G newtons, and the slope makes an angle of arctan 3/4 with the horizontal. Initially, the mass is moving up the slope at 3. Find its speed when it has moved 10 meters up the slope. So here's a diagram. All the forces are on the diagram, notice: reaction, gravity, force pulling, friction. So we need to sort out things carefully before rushing into the work energy equation. AB is 10. We're going to need H, because that is going to be how we calculate our gravitational potential energy. H is 10 sine alpha. Sine alpha is 3/5, so that is 6. If I resolve perpendicular to the slope, I will get that R is equal to 5G cos alpha. Cos alpha is 4/5, that's just 4G. We know that the friction force is 0.8 G. We're starting with a speed of U, which is 3, and we want to find the final speed, V. Well, there's the problem. I don't think we need the written bits any longer. I think that will give us as much as we need, if I can get it to stay up there. Right, let's look at each force. The work done by R. Well, the particle or the ball is moving up the slope. R is perpendicular to the motion. There is no movement in the direction of R. All the movement is perpendicular to R. There's no movement in the direction of R. The work done by R, therefore, is 0, since it is perpendicular to the motion. Make that just a bit more space. What about friction? Work done by friction is, well, the magnitude of the friction force is 0.8 G. and it is moving a distance of 10 AB times 10, that is 8G. I don't actually worry at this particular stage about the plus or the minus. When I come to put that into my work energy equation, it will be slowing things down. It will go in as negative. It's common sense, I hope. We have the 50 newtons force. This is also going through a distance of 10, so that is 50 times 10, that is 500. And again, I'm not going to worry whether I'm plus or minus at this stage. That is making it go faster, it's pulling it, so that when I come in, that's going to be increasing the energy. So when we put that into the equation, it's going to go in as plus. Work done by gravity is GPE, gravitational potential energy. That is always mgh, which is why we worked out h at the top. The mass is 5 times g times h is 6, that is 30g. And again, I'm not worried at this moment whether I put that in as plus or minus, or whether I write it as plus or minus. Now let's look at the work energy equation. This is final KE equals initial KE and then in a shortened form, I tend to write plus or minus work done. So what's my final KE? Well, I come back there. V is my final speed. The mass is 5, and so I have a half times 5 times V squared. Initial KE, initially moving at 3. So my initial KE is a half times the mass times 3 squared. Now let's come to the forces and the work done. That's nice. R0, don't have to worry about that one. Work done by friction is 8G. Friction slows it down. Friction reduces the speed, reduces the kinetic energy. The work done by friction is going to go in as negative. Minus 8G. And now we have the pulling of the rope, the 50 newtons. That is obviously tending to increase the speed. So that is giving us more energy. So that has got to go in as plus. Now, gravitational potential energy, you have to be slightly careful. It's not a difficult thing to cope with. In this case, we're going uphill. If you look at the slope, we're moving uphill. So gravity will be slowing it down. My GPE of 30G will be making it go more slowly. So that is minus 30G. Very easy, really, if you just stop for a moment and don't rush the figures onto a piece of paper. Have we looked at all the forces? Yes. We haven't got any more forces. R did no work, 50, friction, gravity, we've done. All we have to do now is press the buttons, and we get that V is equal to 7.7485, ... which then means that I'm going to say 7.7 meters per second, two significant figures, because I'm using G, and we shouldn't really give more than 2. So work energy equation, it's a very nice little trick. Well, it's not a trick, it's a nice way of solving some problems. And in the next video, you will see a problem that would be impossible, or at least very, very complicated to solve without. But you'll have to wait until we do that video. You should do all of the questions on the worksheet which accompanies this video with the work energy equation. And as I've already said, don't rush your way into the equation. Take it steadily, look at each force. Does it want a plus or a minus?